Okay, so can you see the slides? Okay, so good morning, everybody. Today I will present this new architecture developed by Meta, namely LCM, that stands for Large Concept Models. I am an HPC data engineer here in Cineca, and my work mainly focuses on scaling large AI models, generative AI models on our infrastructure. So first of all, I would like to do a brief recap of what an LLM is for those of you who are not so familiar with LLM's architecture, because I would like to underline the main differences between LCMs and LLMs. So just a very quick recap on LLMs. So the LLM takes in input a text, and that text is split into words or subwords. This process is the tokenization process, in which a text is split into words or subwords, and then these words or subwords are converted into numbers. However, since you want to somehow encode in your architecture the similarity between words, for example, you would like to have cat, the word cat and the word dog near together in some space, you need to introduce the embedding. Embedding is nothing but this conversion of tokens into vectors that encode the semantic similarity between words. And then these embeddings are fed into your model, an LLM model that predicts the next token. Okay, so basically an LLM works with words or subwords, so tokens, and predicts in output tokens. LLMs are known as somehow stochastic parrots because because of this process that I mentioned. However, human brain usually does not operate at a word or subword level. And this is why the meta researchers wanted to introduce a new architecture that operates in a more similar way to the human brain. They stand that they would like to create a model that is able to elaborate and produce concepts instead of words or subwords. And this is what large concept models do. So instead of using tokens, we're using concepts. And so now you are maybe asking, okay, is this the unique novelty that is introduced in this paper, in the LCM? Well, actually, this is not the only innovation introduced in this paper. Obviously, the main innovation introduced in the LCMs is the fact that they work with concepts instead of tokens. But they are also able to be language independent because the text is first converted into vectors that are language agnostic. And this is one of the main differences with LLMs. In LLMs, embeddings are not language agnostic, while in large concept models, the vectors are language agnostic. Is there a problem with the presentation? I'm seeing, are you seeing the slide just concepts instead of tokens, or is there some issue? I see raised hand. Yes, please. Okay, everything fine. Okay. Okay, perfect, perfect. Thanks for the feedbacks. Okay, so I was saying that in LCMs, the one of the most important facts is that LCMs are language independent, and we will see it in detail in few slides. The second innovation is that LCMs are able to handle better the longer sequences. LLMs have this huge problem with the attention mechanism, because with the attention mechanism you have an increase of the cost, because the attention mechanism has a quadratic cost with respect to the context size, and using LCMs and using sentences, concepts instead of tokens enables you to reduce this cost. And we will see also this part. The third important fact is that LCMs helps you avoiding multimodality competition. The concept encoders and decoders are developed independently and can be optimized in a separate way. And so you don't have this multimodality competition that is common in other frameworks. So these are three important facts that I would like to highlight in the whole presentation. So let's start with the training process of LCMs, that as for LLMs as three main parts: the data preparation, the model definition, and then the training part. So let's start with the data preparation. What we need to do in this part is defining what a concept is. So basically, a concept is a sentence. So first of all, we need to do sentence segmentation. The sentence segmentation can be done in different ways. And for example, the meta research team uses for their model the segment any text. That is able to overcome some of the main problems of the sentence segmentations. In fact, it has the segment any text has three main characteristics: robustness to missing punctuation, effective adaptability to new domains, and also high efficiency. So this is why they wanted to use the segment any text instead of other sentence segmentation tools like spacing. Okay, so the first part is done. The first part of the data preparation is done because from a text, we have obtained a list of sentences. Now, what we need to do is the second part, which is what in LLMs is the embedding part, okay? So we need to move from concepts to vectors. And we do this by using the sonar architecture. The sonar architecture is an architecture that enables you to embed these sentences into fixed size vectors. So basically what you're performing, I hope you can see here, if you have a sentence that states, I'll go to the gym starting tomorrow, then what the sonar does is take this sentence and embed it in this space. This embedding enables you to represent any data points, not only text, in a high-dimensional vector space, such that semantically similar data points are close to each other. So here you are doing exactly the same of what you were doing in the embedding part of LLMs, okay? Obviously, the sonar architecture is also used in the last part of the large concept model. So in the first part, you're using the sonar to move from a sentence to a fixed size vector, and in the last part, you're using in the other way. So for going from a fixed size vector to a sentence in the language you chose. So this is one of the most important parts of LCMs, because it is what gives the language independence to the LCMs. So the LCM is language independent because the translation in a specific language is handled by this sonar architecture that is put at the beginning and at the end of the LCM. Okay, now the second part. So the data preparation part is done. Now we need to define the model. So we need to define what an LCM is. In the paper where they presented several LCMs architectures, I will mention just 3 of them. The first one is the base LCM. The base LCM is nothing but an LLM that works with concepts instead of tokens. So it works exactly the same. It relies on a transformer architecture, and the procedure is almost the same. But the fact is that unlike LLMs that learn a distribution for the next token prediction, LCM is trained to output a very specific concept. So in some way, they are similar to diffusion models. Because there are many concepts that could make sense in a given context. And so this is the reason behind diffusion-based LCMs, sorry. Because, for example, if you think of image generation, when you write down, okay, create an image of a cute cat, there are several images of cute cats that can fit in your description, okay? And somehow with LCMs, it's almost the same, because you're predicting sentences instead of tokens. And so this is why researchers have introduced in the LCMs, in the base LCM, some process of forward noising and reverse denoising, which is something that is pretty common in the models that generate images. Okay. So there are 2 types of these diffusion LCMs, and the main difference is how they handle the generative process and the noise. Okay. In the one-tower diffusion LCMs, there is a single transformer backbone that handles both the context and the prediction. So it handles the context, the denoising part, and the prediction. On the 2-tower diffusion LCM, you're separating these 2 parts. So there is a first part that handles the context and is called contextualizer, and the other one handles the denoising process, and this part is called denoiser. Okay. So in the one-tower LCM, the task of the model is to predict the clean next sentence embedding given a noisy input conditioned on previous clean sentence embeddings. So the previous sentences are clean without noise, then you have the noisy input, and then you need to predict something which doesn't have the noise. So you need to handle both the denoising part and the contextualizer both together. While in the 2-tower diffusion LCMs, these 2 parts are handled separately. This is the main differences between these 2 architectures. Okay, so these were the models that were presented. Just a quick note, side note. These models are really small with respect to the state-of-the-art LLMs. We are talking about 1 billion models up to 7 billion models, okay, which is pretty small if you compare them to state-of-the-art LLMs. Okay, now we need to move to training. We've defined the architectures. We've said that there is a base LCM that is almost like LLMs, but without the with concepts instead of tokens. And then there are two new architectures that are the diffusion LCMs. So now we want to see how these models are trained. Okay, so as you can see, I've reported here some metrics that are used and some loss functions that are used to train the model, but I will highlight only some of them. Something that I want to highlight is the difference between the L2 classic L2 distance and the L2 distance plus this encoding decoding part. So here in the L2 distance, you're just measuring the difference between the predicted output and the ground truth. While on the other L2 distance plus encoding decoding, you are somehow measuring the error introduced by the sonar, by the encoding and decoding procedure. Okay. Obviously, if the output generated is not out of the distribution, L2 and L2R are pretty similar. But if the output generated is out of the distribution, this means that the sonar part can introduce some errors, and this is why you want to track both of them, both the L2 and the L2R norm. On the other side, if you want to test the ability of the model in the summarization, you can both test these models on the summarization with different metrics like target similarity, source similarity, fluency, and so on. And also they've tested these models on summary expansion. So you give the model a summary, and then the model is able to expand that summary and is able to add some information. Okay, now I will present you some nice results. The first one is the inference efficiency of the LCMs. As you can see, they compared the 2-tower LCM 1.6 billion, the 2-tower LCM 7 billion, and the Llama 2 7 billion. As I was mentioning before, these are small models with respect to the state-of-the-art of LLMs. So what you can see here is that if the total context size in tokens is really small, then the LCM performs almost like the LLM. But the advantage is really evident when the total context size in tokens, both of the prompt and the answer, increases. So as you can see here, this quadratic shape of the inference flops is due to the attention mechanism I was mentioning before. The attention mechanism has a quadratic cost. And here what you're doing with LCMs is reducing this cost. Because remember, with LCMs, you're using sentences instead of tokens. And using sentences instead of tokens means gaining one order of magnitude, okay? One sentence can be, for example, 10, 20 or more tokens, okay? So this is the first huge advantage in using LCMs with respect to LLMs. The second one which is an extremely powerful result, is the ability of the LCMs to perform really well on new languages. So what they did here is they compared the performances with of the two-tower LCM 7 billion with the Llama 3.18 billion. Llama 3.18 billion supports officially 8 languages: English, German, French, Italian, Portuguese, Hindi, Spanish, and Thai. And according to the Llama 3 team, the model has seen many additional languages during pre-training, but was instruction fine-tuned only on those 8 languages I was mentioning before. And this is why they said that it officially supports only 8 languages. The LCM on the other side has never seen any other language than English. So as you can see, it outperforms the Llama 3.18 billion on Vietnamese, for example. That is a language that hasn't been seen both by the LCM and the LLM. But it has nice results also on other languages that Llama 3.18b has seen and the LCM has never seen. This is due to the sonar architecture, because the sonar architecture is the architecture that handles the translation from concepts into specific languages. Obviously, the sonar has been trained on 200 languages. It supports 200 languages, but the nice aspect of LCM is that the LCM itself, without the sonar part, has only been trained on English. So it has incredibly good performances on many languages that has never seen before. Okay, so there are some more minutes left, and I would like you to recap a little bit what we have said in this seminar. This was just an overview of a really interesting paper released by Meta in 2024, at the end of 2024, that introduced the LCM architecture. So the main differences between the LLMs and the LCMs is that the LLMs work at a token level, while the LCMs work at a concept level. And so the input representation is pretty different. Because in the LCM, you have the sentence embeddings that is handled by the sonar architecture. The output generation is obviously different because in the LLMs it's token by token, so subword by subword or word by word, and the other is sentence by sentence. And this brings to a higher inference efficiency of the LCMs. As we've seen in the previous slide, the LCMs has a great ability in zero-shot generalization. It is able to handle languages that have never seen before in the training part. It is more efficient with long context, while LLMs struggles with long context because of the attention mechanism. And the last one, LCMs are really flexible, because if you want to add a language, then you only need to train the sonar part. So the concept, the learning procedure of the concept generation is itself language agnostic. And if you want to translate this concept in a specific language that is not supported by Sonar, you can simply retrain the first part and the last part. So the Sonar architecture to support that language, and you've done. That is much easier than what you have to do with LLMs. So with this recap, I think it's all from my side. I really want to thank you all for your participation and attention.